Okay. Good morning to everybody. Yeah, I see now that the time is to start, even though I don't see many students, but it doesn't matter. It could be that somebody will join later. Okay, as I told you last time, today we will reconsider a little bit more in a theoretical form, let me say, but not much, the concept of eigenvalues. I don't want to be really boring introducing also eigenvectors. It could be that in this slide you can find them, but for this course at this moment, this is enough to consider the eigenvalues. Of course, in some courses, let me say, the structure of the lecture is a little bit different. I mean, sometimes also in different courses, I start with the more theoretical aspects or methodological aspects, introducing the eigenvalues, and then yeah, we will try to do some applications. But here again, dynamical systems is an intersection between mathematics, system theory, and control. This means you should already know the concept of eigenvalue. Therefore, I try to present applications, giving you some intuitive interpretations. Do you remember? A dominant time constant related to eigenvalues and so on. Also today, even though we will see something more a little bit methodologically, in order to justify, do you remember, determinant of lambda e minus a equals 0, in order to calculate the eigenvalue of a matrix A, which correspond, these eigenvalues correspond to the exponential, let me say, constant of the exponential function of the solution of the differential equations. Excuse me for this long sentence, but in order to recall you your knowledge in Math 1, Math 2, and so on. It could be that you know already this formula to calculate the eigenvalue, but the idea in this context to show you how we can derive this formula, how we can interpret this formula, starting from an example. Again, because dynamical systems, the wording, dynamical system, as I told you at the beginning, recalled as I would like to say, application in the sense of this intersection, which I already told you, between different fields. Let me open the lecture. You have the lecture My Study. Again, the file, the name of the file is session 03. The reason is always the same, because the material comes for different courses, for the reason which I already explained many times, this intersection between different fields or different modules in any case. And as I told you, sometimes I change a little bit the content, even though this lecture here is, let me see, okay. Is always present, this lecture here. I don't know if you see now the presentation. I have problem with the mouse, I have problem with Zoom today. This is really, I cannot click. I don't understand why, really. I hope you can see the presentation. As I told you, this lecture here is in this format. I don't understand. Let me close, let me open again, because I'm not satisfied with this format. Zoom. This lecture is always present in each semester, because, yeah, it's in my opinion, a good connection the mouse doesn't work. It doesn't work, I think. Okay, I would like to. I don't know why the mouse doesn't work. I hope that you can see the presentation, but I don't know why it's in this form, but I cannot change. No, this is not so nice. I don't know why today appear in this form. I cannot improve. Probably now. Okay, now it is better. It seems that the mouse doesn't work or doesn't work correctly. Okay, this is the lecture which you can find in my study. As I told you, the lecture sum up everything which I more intuitively told you about the eigenvalues, about the stability, about the oscillation analysis. In fact, we can see in this slide analytical analysis, but it's not much more with respect which I already told you. But I would like to conclude, to sum up with this presentation, with at least formally is a little bit, I don't want to say more structured, but anyway, you can find everything here in this slide again. Everything in the sense, yeah, probably during the lectures on this topic, I did something more. It could be, do you remember, I presented different cases, explaining the many concepts of related to the dominant time constants and so on. Nevertheless, as always, I start, we can see here, I start considering an example. This example is known. We have seen this example. This means should be easy to follow me in the sense. No? Let me sum up the concept which you already told you many times. We have a system, which we can see here on the upper part, on the left corner, yeah? in the left up corner, let me say, of the slide. And a model. It's a model because it's a graphical model, no? Which we have an inductance, and resistance, and capacitance, or if you want, capacitor, resistor, and coil, in this configuration, in this geometric configuration, let me say so. We have an input U1, I think it's written, yeah, U1, and we considered here the output I1. No? This means in the sense of system theory, we oriented the system somehow. Oriented means in this context here, in the concept of system theory, that I have an input, I have an output. It could be also that I can consider more than input. It's not the case, I would like to say. But I can consider here, for instance, more than one output. This could be not a possible orientation, but in any case, not necessarily I can choose the current I1. The current I1 is the current on the coil, no? As a possible output. Orientation means I have to choose when I choose input and output, or the inputs and outputs. I have an oriented system in the sense that I have an input, I have an output, so in this sense. The state variable or variables somehow we can also choose, yeah, but should reflect in the sense we don't have many freedom, degree of freedom to choose the state variable, because must reflect the energy. Yeah, the natural choice of the state variables is inductance I1 and capacitor voltage U2. Why that? Because it's easy to represent the energy which we have in the system. We have two independent energies. About the concept of independence of the energy, I told you a little bit once, I think, in order to obtain a minimal form of the model in the sense. Here we don't have doubts because we have an electromagnetic energy because of the presence of the coil, and the electrostatic energy because of the presence of the capacitor. This means we have two energies and they are independent in the sense. But of course, you remember the example. If I have a series of a capacitor or a series of inductance or parallel, of course, in this sense, we can think that the energy are not independent. Here again, not necessarily we can be able to consider the voltage in the capacitor. We can consider also the current in the capacitor, but the expression it is a little bit more complex, and in accordance what we want to attain in the form of let me say of control of system theory, the representation of the system is, as I told you many times, is useful to choose is this the voltage in the capacitance or the capacitor, the current and the coil. The practical reason is the energy is directly depending on the capacity, on the voltage, if I consider the electrostatic energy, and is directly depending on of the current, I consider electromagnetic energy. And you remember multiply L multiply current square is the electromagnetic energy. And the electrostatic energy is 1 divided to C multiply U2 in this case square. Anyway, you know, but I repeated this is useful nevertheless. Look at these two equations. We have seen, I think, a couple times. I don't want to repeat this, but they come from the Kirchhoff laws. Remember, I told you a lot about this system. The idea is to use this system here to conclude, to sum up the dynamics of the linear system, consider the eigenvalues. This equation here, the second one, let me say y equal y1 of t, is basically the output. I don't know if you remember the output equation, which again has the dynamical equation, which is this one, x dot. We can see x dot is the state vector, which consists in our case I1 and U2. Again, yt in this case is I1, but of course I can consider any kind of variable. Please pay attention, not only in general the state variable. Everything which is can be interesting for us to be monitored can be considered as an output. Again, the equation, the second equation is always as the dynamics as a function of the state x, state vector x, and the input. Because the energy, basically, do you remember the concept? This one changes with respect to the input, what I am doing, and the state of the system, the energy which I store in the system, let me say, at the time t. Now, let me consider U input equals 0. In general, U input is the input. In our case, is U1. But why I put a U input? Because could be any kind of input in the general expression. In our case, U input in accordance with this nomenclature is U1. It could be that during the semester I used many times U input. U input is in this case is U1. Now we can see an input variable U1, the external voltage. External because we have seen also many times during the last 2 weeks, U1 comes from the controller. The controller is considered somehow an external element. Let me call element with respect of the system. You remember, no external solicitations, no inputs. No inputs is not so. It's colloquially correct, but it means input equals 0. No? Please pay attention. It is colloquially, we can say no inputs, but it's not exactly correct. Means inputs equal 0. You remember, this is related to the concept of the free answer. Do you remember at the beginning of the semester, I told you a lot about the free answer. This is basically we want to analyze the system, let me say internally, no? Remember, internally means that I want to see how change the states just as a function of the initial conditions. Remember the definition of the free answer. Input equals 0. I don't want to say no inputs. Yeah, it's a little bit strange. But anyway, if no inputs means inputs equal 0, this means okay. But we have the initial conditions. Now, the general equation, which you can see here, x dot equals a, which multiply x plus b multiply u1 or u input, becomes this in general. In general, we will see that a remains for this example, this matrix here, in which x again is the current I1. Here I put just I. This is a little bit not precise. It should be I1. Yeah, it could be that I mistake in LaTeX. And x derivative is the derivative of this vector here. This means the derivative of each component, in the sense. Yeah, let me analyze the internal stability. I told you about the internal stability many times. Basically, we want to analyze the free answer. We are in the presence of a homogeneous differential equation. In order to equations, in general, we have equations, two equations, but it's the homogeneous case. If I say differential equation is nevertheless correct, it's nevertheless correct because in a system of differential equations of first order correspond of a differential equation of the second order. Probably you did with math, but it's, at this moment it's not relevant to go in depth on this, just to recall it. Again, the hypothesis here that lambda 1 is different to lambda 2. We have two eigenvalues because we have two equations. This probably you have seen in math. But let me assume that lambda 1 is not equal to lambda 2. This case, I think I have in this slide. Otherwise, I can find the slide in order to analyze this case here, lambda 1 equal lambda 2, even though in a practical sense, is not extremely relevant because is in a mathematical condition. Lambda 1 equal lambda 2, or if I say something equal something different, is clear equal. The equality is in a mathematical condition. Practically, in the applications, let me say, it's not possible to have this condition. Nevertheless, in a condition can be used as a model, as something which we want to tend, as an ideal condition. Could be. But let me consider now lambda 1 different to lambda 2. Let me see if I have it here, or if I have it to look. Another slide. No, I don't have here, but I can tell you nevertheless later. Okay, look what I'm doing now. I don't know if you remember the analysis of the free answer. You remember, I suppose that the solution consists of an exponential function. Here, this E is the exponential function. In some books, you can find EX P, sometimes EXP. Now it's just E. It's an exponential function. Now, X of t, this vector, which I consider a possible solution of these differential equations, or the system of differential equations characterized by the matrix A, let me say, I will consider equals this structure here. Why that? Because I am assuming that I have two different lambda 1 and lambda 2. And I am assuming that in a combination of these two exponential functions characterized by lambda 1 and lambda 2 respectively, a combination, a linear combination, we can see a C1 which multiply this exponential function up to lambda 1 multiply t, plus C2 multiply this exponential function up to lambda 2t, represent can represent the free answer of I1, because I1 is the first state. And the second line, another linear combination, again, of the same exponential function, but consider a different constant, C3 and C4. This means a different linear combination of the same function represent the solution for U2. Solution in the sense is the profile, is the, in the second case is the voltage with respect to the time. In the first case, and the first state is the current I1 with respect to the time. Now, assuming that is exactly the assumption which I did, probably is a little bit in different form when we started with free answer and the fourth answer. Here is a little bit more structured, but now we have we are able to understand this concept of the linear combination of these eigenfunctions. But anyway, let me assume. I can assume whatever I want. And then at the end, I will show you that my assumptions, first of all, let me say, solve, colloquially speaking, these assumptions solve the problem. The problem here is to find the U1 of t and U2 of t. This means the current I1 with respect to the time, and the voltage U2 with respect to the time. For the free answer, this means for I1 equals 0. Of course, considering some initial conditions, which I didn't put here, but must be there. You remember, and the free answer must be there in the sense should be not 0. Because if they are 0, we have the free answer is 0, because no energy, no external energy, no internal energy, of course, the energy remains at 0. Okay, this expression here can be written in this form. This is, if you remember a little bit, the rule of the product of matrices with a vector. Row multiply column, row multiply column. I don't know if you remember this, but it's easy to see, no? C1 multiply exponential function plus C2 multiply exponential function. I have the first element of the column vector, which is the result of the product of this matrix 2 times 2 multiply this vector 2 times 1. And of course here, if you do row multiply column, I have a C3 multiply exponential function plus C4 exponential function. This means I already justify why I'm writing this form here. Now, the matrix which consists of these 4 constants, C1, C2, C3, C4, I can call C just for sake of brevity. This means my x dot. Do you remember at the beginning? Excuse me here if I forgot I1. No, but this I1 is not I. Very important, not only x but also x derivative, because this fundamental equation here, which states the free answer consists of x, consists of a, consists of x dot. A we know, x also we know. Now I have to also calculate the x dot in form of solution. We can see here. Starting from this assumption, the assumption of x derivative is this one. It's easy to remember just recalling the rules or the rule of the derivative of an exponential function. I think I don't have to justify. I mean, the derivative of an exponential function up to lambda t is lambda multiply the exponential function up to lambda t. Do you remember this? I apply this rule here. Equal C, because I can use the same property. I don't know how we can say trick, if you like. C, which multiply the identity matrix. It's not exactly an identity matrix. The matrix consisting of eigenvalue lambda 1 and lambda 2. I don't know if it's if it's visible in the sense. Let me see what I can. Mhm. I don't know if it's visible because C multiply, let me say, this matrix here is again as a matrix 2 times 2, no? Because we have a C as a matrix 2 times 2, multiply with this particular matrix here in the middle, which consists of, as in a diagonal matrix, in the diagonal we have lambda 1 and lambda 2, is again in a matrix 2 times 2. In which basically we have something like here, but C1 multiply lambda 1, C2 multiply lambda 2, yeah, C3 multiply lambda 1, C4 multiply lambda 2. Believe me, but if you don't believe, do please the calculation at home, but it's extremely easy. No? And the product of two matrix, 2 times 2. If you imagine here C equals C1, C2, C3, C4, rho multiply column have a C multiply Y1 as the first element of the 2 times 2 matrix. The second element, in the sense the element 1, 2 is C2 multiply lambda 2. And if you do the same for the second row, you will obtain C3 multiply lambda 1, and then in the position 2 times 2, we have a C4 multiply lambda 2. And then if you do again the multiplication, we will obtain this. Try to do at home, but it's easy to see also just looking for, yeah, looking directly on at the definition of the product, and then considering C again as net 2 times 2 matrix, C2, C3, C4, C3, C4. Right. This means we have this expression here. I copied for you in this slide again. Which is the derivative of the state space. Let me see. At the end, the space of the state space vector. Excuse me, I forgot vector. Again, this x dot is this expression clear. I try to explain without doing the calculations. If it's not clear, I can do. I don't know if I have here. Yeah, something to write. Let me see. Let me find some, because I see that probably is not so clear. Let me show. I find quickly using to write. Let me see. I don't have good things to write again. Let me see if I find something to write. Yeah, I don't know if it's right. Let me write. Let me try. This mouse doesn't work. You see? This was the derivative of the component of the vector x. Exponent, just to show you again, to change the notation to be more flexible, no? In order to show you that in some books, instead of E, you find EXP. Row multiply column. This multiply this, plus this multiply this. And here we have row multiply column. I don't know if it's visible. Excuse me. It's not ready, no? I would like to do fast. Here remain. Today, I'd like to do too fast. And here, again, row multiply column. Row multiply column. And this is clear, no? Row multiply column. And here, now, let me complete, but it's not a problem not to understand this. Equals this one. And this expression here was our original expression which state the derivative, but very important, very important. I mean, to write this expression in this form here, the expression of x dot. Let me come back to the lecture now. I try to explain quickly. Now we understood better why this expression can be written in this form. Again, now x dot, we demonstrated is equal to this one because the matrix C1, C2, C3, C3, C4 we call C. This means we can write x dot in this form here equals A multiply C multiply this vector here. Why that? Because x we wrote in this form here. Excuse me for the mismatch in the notation here. C, this 2C here collapsing, this is C bold, let me say. Not cursive as bold, but it's the same C, believe me. No? This the matrix of the constant C1, C2, C3, C4. I don't know if it's clear. This is x dot, and this is A multiply x, because I would like to represent this expression here, which is the basic expression in terms of system of my free answer. I don't know if it's clear. C multiplied this vector here is x. This means A multiply x is this part of the equation. X dot can be written in this form here. Now, why now this expression here? Because if you remember the exponential function, I told you also when we talked together about the free answer. The exponential function is a function which is never zero. Just asymptotically, it's going to zero. Assuming that lambda 1 and lambda 2 consist of negative real part, is going to zero if t is going to infinite. If lambda 1 and lambda 2 are positive part, in this case, the exponential function is going to zero for t toward minus infinite. In any case, it's never zero. This means I can cancel left and right. Remember, as if I do a simplification, I can divide it. Here, the division is a little bit formal, but we did a little bit this together in another context. This means this equation here is equivalent to this equation here. because let me say left and right, we have something which is equal. It is never 0. Now, from this expression, I can write in this form. It is easy to see that I bring on the left part AC, and this means this element minus AC equals 0, no? Because we have this we have an equality here. No? This means C, which multiply now this particular matrix lambda 1, 0, 0, lambda 2, and then minus this this expression here. Why that? Because here I put in evidence on the left the matrix C. Do you remember? Multiply on the left is not the same with respect to multiply on the right, no? In the differential, let me say, in the product of matrices. This means here I wrote, in order to obtain the equality, I put here C up to -1. Again, if you put in evidence on the left C from this expression, I will have this expression here, assuming that C is invertible. Assuming that C is invertible. Otherwise, I cannot write C up to -1. Do you remember the matrix is invertible if the determinant, I don't know if you remember math, is not 0? This means practically that the column or the rows, the columns of the row are not depending. The columns of the row are not depending. This means somehow, what I will say means directly that these eigenfunctions are not depending somehow. No? The combination of the eigenfunctions is not depending. No, this is an interesting concept, but they are not depending because they are different. No? We have lambda 1 and lambda 2. No? This means, again, we are not considering lambda 1 equal lambda 2. Otherwise, we have two functions which is depending. But anyway, assuming that it's invertible. Look, we have this expression here. Now, from this expression here, which I put again here at the end of this slide, if C is invertible, I can, in this case, multiply by C up to -1 this expression here, and I will obtain this. I don't know if it's clear. I multiply on the left up from C up to -1. I will cancel C. I will obtain this. Clear, no? Assuming that C is invertible. Again, the expression which I have. Again, the expression which I have. Let me consider now the general matrix as follows here, no? Which we have this basically this equation here. If I have lambda 1 and lambda 2, must be satisfied considering to calculating the matrix C. Let me now, for a while, considering a general lambda, is a general lambda in this form here, and let me write now this expression here in this form, quite general, without specifying lambda 1 and lambda 2. This I copy for you. This expression here again. Now the question is basically, when does this algebraic linear system admit not zero solutions? Zero solution with respect to C. This is the problem. If you don't like, let me say, if you don't like this general expression, you can remain with this. We can remain with this. The question is, when we have as a matrix C not zero. Look at this. I don't know if you remember. I don't know if you remember the concept of the determinant. The idea is we have not zero solution in C if the determinant of this expression is equal to 0. I'm looking for C1, C2, C3, C4. It could be that this position here, let me, if you don't like this, but we will see that this is useful, think about this. Then think about to find C1, C2, C3, C4. Not 0. The condition, I don't know if you remember, in solution of the algebraic system is that the determinant of my system should be 0. In this case, we don't have the solution in a linear system, let me say, totally 0, totally 0. All zeros. This means, because in a linear system, if the determinant is not 0, or better to say, it's 0, in this case, we don't have the solution 0. We have something consistent in this set, or at least not 0. This means if this is the condition which came from math, I can write this expression here in this form, because I put in evidence left and right. We can see here. Left, I put in evidence C up to -1, and right, I put in evidence C. I don't know if it's visible that this expression here inside the parentheses is equal to this one. Why that? Because C up to -1 multiply C, or better to say, C up to -1 multiply lambda I multiply C is equal lambda I. Because here is an identity matrix. It works also if I have a lambda 1 and lambda 2. Just more generally, I didn't consider lambda 1 and lambda 2. And here, of course, remain A, because again, I put in evidence C on the C up to -1 on the left and C on the right. Equal 0 remain. This means determinant of lambda E minus A equals 0, representing not trivial solutions, the condition of not trivial solution from C. Trivial solution means everything 0. This means also that C is invertible if this solution is satisfied. Now, in order to clarify from here to here, I put this note. Is a property of the determinant. Is a property of the determinant. Because if you look at this expression here, we have the determinant of the product of 3 elements, matrix is better to say, and this is the product of the 3 determinants. In which the determinant of C up to -1 equals 1 divided the determinant of C. The determinant of C up to -1 equals 1 divided the determinant of C, which I can cancel with this. We can see here. The determinant is in a scalar. Determinant is in a scalar. Let me see if I can explain a little bit better. This is basically the condition which we applied last time. At the end, I summarize everything. So do you remember we applied this concept many times, also last time. This is exactly what we have seen. What we have seen. We considered different systems, also in different contexts. also in the design of the controller. Let me insist a little bit before take a rest. Again, let me see if I can. Let me come back to the lecture. Um, um, Look at this again. If you don't like this expression here, which is more general, remain on this. Assuming that I have lambda 1 and lambda 2. The idea is to find when this equation is satisfied with C not trivial, with C not zero. And I don't know if you remember one condition. C not zero is not acceptable for us for many reasons, because first of all, it's not a solution. Secondly, we assume that C must be invertible. And where come from this idea? This works also with lambda 1 and lambda 2. No? If you write everything in terms of lambda 1 and lambda 2, this came from the condition that in a linear system, of course, is a linear system in terms of C1 and C2. Let me see if I can express. This could be a little bit difficult to be understood. It's a shame I didn't write here my thing. But if you assume that we know lambda 1 and lambda 2, of course, in any case, lambda 1 and lambda 2 are given. We have to find C1 and C2, C3 and C4. Now we can see from probably better from here. A is given. Lambda 1 and lambda 2 is given. Look here. Or better here. Here. And if you remember, the condition is determinant equals 0. If the determinant equals 0, we avoid the trivial solution. No trivial solutions in this sense. And of course, from here to here is in the technical in the sense we have to recall the property of the determinant. So this expression here, we have seen can be written this form here, put in evidence on the left C up to -1, put in evidence on the right C. And then, of course, we have here the determinant of product of matrices, which equals the product of the determinant of each matrix. But we know that the determinant of C up to -1 is 1 divided the determinant of C. Determinant of a matrix in a scalar. Therefore, I can cancel determinant of C up to -1, multiply the determinant of C. Because it's basically is in a product of 3 scalar. Let me see if I can add something more. The independence of the matrix C is given by, let me say, indirectly, because it's in a combination of independent eigenfunctions in a sense. Very important to to prove that it's not zero, the matrix C. And here's the proof. Anyway, we justified now where this expression comes from in general, which holds for each lambda 1 and lambda 2. This is general. Now, can be used in different form, this equation. For instance, here we can see that we can analyze using this equation here, the dynamics of our original system, because we can calculate lambda 1 and lambda 2. But you remember, last time we used in a more complex context, do you remember, to design the controller, given lambda 1 and lambda 2. Given lambda 1 and lambda 2, I can use this equation here, in which you remember this matrix here we called, I don't remember, A minus B multiplied K, remember. The parameterized matrix of the controlled system can be used also for given lambda 1 and lambda 2 for given dynamics, can be used to calculate the parameter of the control. But let me remain on this. Now I can use this determinant lambda I minus A equals 0 to analyze the dynamics of the system here, because the idea is to calculate lambda 1 and lambda 2. Here we have basically this expression here. If I do, let me say here, the determinant of this expression here inside a parenthesis in the matrix. Which matrix? Lambda, the second element is plus 1 divided L. The element 2, 1 is minus 1 divided C. And the element 2 times 2 is lambda plus 1 divided RC. The determinant. This one, I know that you know better than me to do the determinant, not for math 1, math 2. And then if you apply in German, we say PQ formula, no? But you can also apply the ABC formula, in which A is this one, B is this one instead of P, and C is this Q. Anyway, you can use whatever you want, no? To calculate lambda 1 and lambda 2. And in this case, P is 1 divided LC, and Q is 1 divided LC. This means this is lambda 1 and lambda 2, which consist theoretically in a real part and plus minus an imaginary part, if the imaginary part exists. This means we have to look, do you remember? I told you this at the beginning of the semester when we have seen we analyzed the free answer. We have to judge about the sign of this element inside the root. And then we will classify oscillations if we have an imaginary part. Without oscillation, if we don't have in the sense equal 0, or better, positive element under the root. Equal 0 in the particular cases could be, I don't remember if I did at the beginning of the semester, we can do, but it's not at this moment relevant. If I have time at the end of the semester, I will tell you about lambda 1 equal lambda 2. It's not extremely important because practically and physically it does not exist. But in control, sometimes can be used as a reference. But let me go ahead, because after this topic here, we will conclude now. I would like to start the nonlinear systems, and then if I have time, next time, we will see, I can consider lambda 1 equal lambda 2. Lambda 1 equal lambda 2 means this equals 0. No? This means apparently we have two exponential function which is equal. This means in a matrix somehow we have a dependence of the solution, let me say so, but it's not really so. But let me consider this. Let exclude again lambda 1 equal lambda 2. If this is negative, is what we have under the root is negative, we have oscillation. If it's not, we don't have oscillation. I did an example at the beginning of the semester of this. This part here is the real exponential part, always. Could be also, I can add this if it's not negative. And basically, we can classify the following cases. In general, let me say, if I have a real part plus minus j omega, omega is the, let me say, the imaginary part. Basically, omega is root j omega. J omega is root of something negative. You remember, root of -1 equals j. Now, we have oscillations in case omega not 0. If sigma is negative, the system is internally asymptotically stable. About that, I told you, because the solution is going to 0, no? For t going to infinite. With oscillations, if omega is not 0. If omega is 0, we go into 0 without oscillation. Sigma e 0, single solution, not multiple solution. We clarify what I intend. It's exactly what I told you until now. Lambda, let me say, lambda 1 not equal lambda 2. This means we have plus j omega or minus j omega. No? This is two single solution. Two single solution. Just to understand what I intend. We say that the system is marginally stable. I don't know if I told you about that. I don't think so, but it's an ideal case in which we have permanent oscillations. Permanent oscillation. It could be that at the end of this next week, I can tell you a little bit about that. It's also an ideal case, because again, sigma equals 0, something exactly equals 0, practically is not possible in the application, not possible, but could be a reference sometimes for control. Sigma larger than 0 means unstable, no? Because the exponential function at coefficient positive. Here we can see when we have oscillation, I already told you, when we have under the root is negative. This is the condition. Before discussing this expression here, or this graph, which summarizes everything, let me consider here just let me say a little bit the oscillations. We can see, if you consider this expression here, for instance, this expression here, that conceptually, we have oscillation if this is satisfied. This means conceptually, if we have a very large C values, we can see C squared, C on the right part. This means here we have a C, 1 divided R squared C, R squared C, less than 1 divided L. For large C, tendentially, we have oscillations. As for large R. This came from here. No? Or equivalently for small l. No? So just to qualitatively to understand. Please pay attention why large R. It seems to be a little bit a contradiction because R represents losses, but not in this scheme. I am analyzing this scheme here. No? Because large R implies that the energy is going from this point to this point, tendentially, no? The trend, because large R means open circuit, no? Somehow. This is a little bit the why R seems to be is large, no? This sentence here. When we have oscillations here, when the energy is passing, let me say, the exchange of energy between electromagnetic and electrostatic. If R is very small, we don't have this exchange, or we don't have much. Yes, basically what I told you. This is basically what I told you. In case of lambda sigma positive, we see that the solution is going to infinity. With oscillation or without oscillation. On the right, we have exactly the contrary. With oscillation, if we have an imaginary part, not zero, is going to zero. Without oscillation, if the omega is equal to zero. Okay, I would like to stop here. We take a rest, we drink a coffee, and then we will go a little bit more in depth here. On some particular aspects, and if I find material I have here, I think we can speak a little bit about lambda 1 equal lambda 2, and the case also omega equals 0, not to have permanent oscillations. I don't remember if I did, but we can redo. And the idea is that the rest of the lecture I will introduce the nonlinear systems, and then next week we will see a particular form of the control of nonlinear systems. Because in nonlinear system we cannot define the eigenvalues, and then we have to consider a different structure of let me say, to analyze the system. Nevertheless, we have a lecture next week, and then I have to recover one lecture, because once was traveling. This means we have time to complete. Okay, we will see. Let me take, now is the time to take, let me, 10 o'clock, we will come back here. Huh? Okay, let me restart. And let me conclude with this presentation. About this slide, I already told you a lot, which basically we can distinguish between left and right with respect to the imaginary axis. We can see j omega, the imaginary axis. About the imaginary axis, I already told you what I intend. We can see that on the left, we have the asymptotical stability with and without oscillations. This means if I have the imaginary part not zero, plus minus j omega, we have asymptotic stability, but with oscillations, because the real part nevertheless is negative. On the right part of the imaginary axis, we have, we can see in an unstable behavior with or without oscillation, with the same concept, I would like to say. If j omega is not zero, we have oscillations, of course, unstable, because the real part of the eigenvalue is positive. If j omega is equal to 0, let me say omega is equal to 0, in this case, we have unstable situation, but without oscillation. What happens on the imaginary axis? We can see that we have a permanent oscillation in case we have a sigma equals 0, and j omega not 0. And if j omega is 0, we have something constant. If j omega equals 0, but single solution. What is the meaning of single solution? Let me tell you about single solution, not multiple solution. The system is internally stable, but not internally asymptotically stable. Asymptotically stable means that for t toward infinite, the solution, or let me say the answer, the free answer is going to 0. It's not the case. It's also here, it's not the case. It's not 0, no? Here is the same, no? The answer here is the same like here. No differences. I have an example in one of the first lecture, which we have was in a mechanical system. I don't remember which system it was, but I did. Also here, this profile is exactly the same like here. Also here, this here is exactly here. Let me consider this. Again, on the axis is not asymptotically stable, but single solution. Let me show you an example in order to understand uh, what what I intend. Even though it's not my intention to go really in depth, I would like to show you just intuitively because I don't want to tell you about the eigenvectors. Look at the system here, just intuitively. Just intuitively. At the case of multiple solution, we have to distinguish two cases. Eigenvectors are linearly independent. Second case, eigenvectors are linearly independent. I don't know if you remember the eigenvectors of the matrix. If you don't remember, it does not matter. I don't have time now really to tell you about that. I do something. Yeah, I consider this topic here in math for engineers, but is in a course of master. Look at the system here. Just intuitively. X1 derivative by x2, x2 derivative by u of t. Easy system. Another system could be x1 derivative equal u, x2 derivative equal u. Basically, we can see this cascaded system. Now we will see what is the meaning of cascade. This is a parallel system. Look at this. Let me consider the first case. We will see what happens. Keep in mind, eigenvectors are linear dependent, but if you don't remember, I know that you should know the concept of eigenvector, but it's not now the how possible to say the goal to analyze this. Why the system, in your opinion, for instance, is not stable, is unstable. As I told you, in case of a single solution, the system is stable, but not asymptotically stable. Here, sigma equals 0, but we have a multiple solution. I don't know if I have here this. I don't have. This means I will calculate for you this case, both cases you want. Let me consider this. Now write something. Okay, let me switch on the lateral camera. Let me consider this system. Let me see if I have something better to write. You remember, this was u of t, but in the free answer I put 0. Let me realize this in terms of matrix and vector. This is the system characterized by 0, 1, 0, 0. Did you agree? Huh? Excuse me, I don't have a better, or let me see if I have something better to write, because otherwise you cannot see very well. I don't know. if this can help. Let me consider this system. I think you can see a little bit better. Again, this is the matrix A, transition matrix. Let me calculate. Yeah, we have seen also today in a detail form. Determinant of what? So, this implies lambda squared equals 0. This means lambda 1 equal lambda 2 equals 0. You remember, lambda 1 equal lambda 2 is already something which we want to discuss separately, but more, not only equal, equal 1 could be equal 2, equal 0. A particular form. And really in a particular form. Also, lambda 1 equal lambda 2, for instance, minus 1, minus 2 is in a particular form, but this is more particular, no? Because we learned that the 0, also in high school, is in a particular number. We say that the system is not stable, it's unstable. And of course, in order to understand really better, we have to analyze the eigenvector. I don't want to do that. Let me analyze this intuitively. This is x1. This is x2. This is x2 derivative. I don't know if it's clear that this element or this representation here represent the system here. No? X1 derivative equal x2. This means we have a x1 derivative. No? But you can call x2 in accordance what is written here. The integral of the derivative is exactly the function. No? Of course, now the question is the initial conditions. Why this is unstable? Here it's 0. Do you remember the concept of free answer? No? U equals 0 means no input at the center, the input 0. Now, why is this unstable? It's unstable because if we have an initial condition here, equal not 0, of course. For instance, 1. The integral of 1 is in a ramp. This means the system and the free answer, the system here, free answer because this is 0, is not for each initial condition stable. If I put here as initial condition, in this case, is the answer limited, because 1 remain 1, but this 1 is here, the integral of a 1 is in a ramp. This means it's not stable, it's unstable, because not for each initial condition remain limited. This is a little bit an intuitive explanation. To be more precise, we have to analyze the eigenvectors, but I don't have a time to do that. Let me show you now here the other system. Therefore, if the single solution with sigma equals 0, real part equals 0, we don't have problem to say the system is asymptotically stable. But if you have multiple solutions, it depends on the structure. Look here, we have here also multiple solutions. You remember U and U. Huh? You have here multiple solutions. But the system is not cascaded. Do you remember? This is the meaning of cascaded, a cascaded system. With the eigenvector, we can analyze a little bit better, but let me go ahead here in this because I would like to tell you something different now. Different things. This is the transition matrix. And now we can understand this parallel form, not cascaded. Scusa. Determinante. This is lambda I, and this is A. Determinant of lambda I minus A. This means determinant of what? Lambda 0, 0 lambda, right? This means lambda squared equals 0. As before, both systems, this here and this here, have the same polynomial characteristic polynomial, excuse me, with lambda 1 equal lambda 2 equals 0 in both cases. Apparently, they have the same dynamics, but just apparently. Why that? Because analyzing the eigenvectors, I don't want to do. We realize that in this system here, the eigenvectors are independent. In this system here, the eigenvectors are depending. In the other case. Why that practically? We have in a parallel structure. x1 of t, x2 of t, independently of the initial condition, remain limited output. 1 remain 1, 2 remain 2, because the system is not cascaded. This concept of depending and independent eigenvectors is related to the connections. Here is, let me say, interconnected in cascade form. Here is not. I don't have time to analyze the eigenvectors. Basically, I will do this in a course of a master. The course, the name is Math for Engineers. But if you have time in my study, you have a little bit an appendix here, which this appendix is dedicated to the eigenvectors. But anyway, for the examination, it's not relevant to do that. Nevertheless, I would like to conclude saying, two important final considerations related to the stability. Let me consider again this case of single solution for sigma equals 0 on the imaginary axis. If U is not 0, look, I would like to introduce now the concept of BIBO stability. BIBO means bounded input, bounded output. It is the case of U not 0, exactly what I am trying to tell you now. Or external stability. Or if you want force answer, do you remember? Just to reconnect the concept which I introduced at the beginning of the semester. Look at this. If the linear system is internally asymptotically stable, this means sigma definitively negative. It doesn't matter with or without imaginary part. That the system is also externally stable. Externally with BIBO stable. BIBO means bounded input, bounded output. This means a limited input, limited output. Why that? Because the system is structurally stable because of the real part of sigma equals 0. bring the modes, the dynamics to limited value, even we have an input, but of course the input must be limited. This is clear. We can also do some mathematical analysis, but intuitively it's quite clear. But look at this. If the linear system, which I am considering, a linear system, is internally stable, this means sigma equals 0, single solution, then the system is externally Bibo unstable. Why that? The reason is, look at this. Example, no? Did you see in the slide I put example? I show you now here. This is this system here is internally stable, even though we have lambda 1 equal lambda 2 equals 0. But as I told you, practically we have to parallel system. Mathematically, we can demonstrate that the eigenvectors are independent. Independent method that we have means that we have two different directions. One for x1 and one for x2. It try to interpret a little bit some mathematical structure. Here we have just one direction. The eigenvectors which states the eigenvectors state the direction somehow. You have just one direction, two eigenvectors depending. I don't know if you remember in math the concept of the dependence. If I put here the input 1, independently of the initial condition, this is a ramp, because I will integrate 1. This means not for all, but in limited input, we have a limited output. We say that the system is externally unstable or Bibo unstable, just to a little bit to understand also the nomenclature. I think I will conclude now with the presentation. Yeah, because we will start now with the appendix. Think about that. If you want to look at the appendix, there is this concept of the eigenvectors. But I will not include this in the examination because this is a little bit more advanced and so on. Now we take 5-minute rest. In the meantime, I look for some materials related to lambda 1 equal lambda 2, generally, not necessarily equal 0. We have already analyzed. And then the oscillation solution. I think that I will find now. Give me 5 minutes and then we come back. I can do, if I don't find, I can do directly with the hands. But if I find, we can speed up a little bit, because it should be nice if I am able today to start with the nonlinear dynamics. 5 minutes and I come back. Okay, I found material for you in order to speed up this last part of this lecture, and then I think I have time to introduce a little bit the let me see, the nonlinear analysis, which we will do next week. I will fix next week the tutorial, because the exam is almost at the end of the month, of this month. Nevertheless, we have time. Let me now share the lateral camera. Look at the system here. Now I will come back. I will come back on the of a system we can see here, but in form of differential equation. Do you remember I told you that I already analyzed how from this language here we can reformulate everything in terms of matrix and vectors. Do you remember I told you? I mean, we have a differential equation of the second order, which can be equivalently written in system of two equations, but the first order, and then we can write in terms of matrix and vectors. Anyway, let me consider a free answer of this. because we want to analyze the case in which lambda 1 equal lambda 2 at this moment. And then more lambda 1 equal lambda 2 equals 0. You remember, we have to distinguish two cases. In lambda 1 equal lambda 2 equals 0. Eigenvectors depending on eigenvector independent, even though I didn't analyze exactly in depth, but you remember what eigenvectors are. I told you about this dependence, independence, which is related to cascaded, not cascaded. This means that the direction and not separated in the sense. But let me analyze this. This is the case lambda 1 equals lambda 2, but not 0. Free answer, yeah, I can consider an input, but let me write 0. Initial condition, 1, 0. Idea is find the solution. We will see that this particular case, lambda 1 equal lambda 2, not 0. It's not, let me say, in a standard form. Look, let me come back to our original idea to find the solution, which is basically not much different with respect to determinant of lambda e minus a equals 0. But of course, here we don't have a. We will want to proceed in this form, but you can do the same. You can do the same with the determinant of lambda e minus a. I show you. Do you remember? Assuming that this is the form of the solution, eigenfunction. If this is the form of the solution with k not 0, we have the first derivative, which is this one, in accordance with the rule of the derivative, and the second derivative is this one. Plug it in, this, and this here. We have this expression here. We did this example, this analysis many times. We did this analysis many times. Exponential function is always not 0. Remember, this means I can cancel. K, in accordance with this hypothesis, is not 0, because if this is 0, I cannot satisfy this condition. This means from this expression here, I have this characteristic polynomial. Do you remember? This is the name, which can be calculated in the same way. If I consider the expression of this equation here in terms of matrix and vector. If you want, I don't have here, but I can do. So we repeat again this exercise. This is very often also. Excuse me, plus. This is the original system. No? The initial condition I can put, but they remain the same. No? Let me proceed. Excuse me, minus. Minus. I don't know if you agree that this system here is equivalent to this one. The idea is x is equal to x1. This means if I put x1 derivative L x2 derivative is equal x dot dot. I don't know if it's possible to see. The idea is, I told you many times, at the beginning of the semester, to x of t equal x1 of t. If I put now x1 dot equal x2, I have that x2 dot is equal to this one. Why that? Because x2 dot is x dot dot. If I consider this position and this position, but x dot is x2. X dot is x2, because if I dot here, I dot here, and x1 dot is x2. X, I already told you, equal x1. This means this expression can be in equivalent form with this system of two equations of first order, starting from this equation of the second order. This means now x1 derivative, x2 derivative equals matrix A transition matrix to be calculated, x1 of t, x2 of t. What I have to write here? 0, 1, clearly, no? Row, multiply, column. We did this exercise many times. What I have to write here is not so difficult. -1, -2, no? Row, multiply, column. Do you remember? We did a lot of time. I will get this expression here equal x2 dot. Now, determinant of lambda I minus A, I told you a lot about this, no? This means determinant of lambda 0, 0, lambda minus 0, 1, -1, -2 equals 0. Determinant of lambda -1, 1, lambda plus 2 equals 0 means this multiplied this minus this multiplied this. This multiplied this plus 1 because it's this minus this multiplied this, which equals lambda squared plus 2 lambda plus 1 equals 0. This is the characteristic polynomial associated to this differential equation, or the system of differential equations, which is associated in the same way to this differential equation. Because do you remember? This expression here is equivalent, totally equivalent to this one. The initial conditions must be the same, is the same. But this polynomial, this characteristic polynomial, lambda squared plus 2 lambda plus 1, is the same which we obtained using the first method. You remember, assuming that exponential function and so on. You can do both. This expression here can be written in this form here, in which we have lambda 1 equal lambda 2, not 0, but equals -1. This means we have something which reflects the asymptotic stability, but anyway, they are the same. This means, you remember the concept I sketched just a little bit, I told you about a little bit about the dependence of the eigenfunctions. If you consider this now, I try to comment this sentence here. No? It's as if we have just one eigenfunction. But the system consists of, let me say, two dynamics, if you want. No? You remember at the beginning I told you system of the second order, second with two derivatives. You know, let me say means it means that we have two energies. It's that we have two states independent. In the sense, it seems to be that we have just one. Let me see now what happens in this case. Just a second. Exactly. I already commented this quantity that we have just an exponential function because they overlap. But theoretically, the system reflects two energies, two states. It seems to be that we have a mismatch. Let me see how we can solve. I think at the beginning of the semester I told you about. What is the assumption which limits, in our case, to see that we have two states? This K. I wrote here K isn't a constant. Assume that K isn't a constant. Is in a constant. Of course, it's a limitation because um, again, the derivative of the exponential function is again exponential function, but k is a constant, could represent a limitation. I mean, why that? Because if k of t, for instance, is a polynomial, the derivative of the polynomial is again a polynomial. You remember why I'm assuming that the exponential function is an impossible solution? Because the derivative of an exponential function is an exponential function, the second derivative of exponential function is exponential function. I can think that this condition is satisfied by an exponential function. But in the same way, I can think that let me say, the solution could be something related to the polynomial, because the derivative of the polynomial is again a polynomial. Okay, let me try. There is also a different interpretation, but remains so. Let me try to this. I don't know if this is clear. Also, this sentence is interesting, no? Because we have just an exponential function, and I have to satisfy two conditions. Now, let me try with this. Because we have, in this case, the possibility to distinguish, thanks to this element here, the two exponential functions. But this element here, assuming that is a polynomial, could help because the derivative of the polynomial is again a polynomial. Let me now take something. This means the first derivative of x, considering x of t equal k of t exponential function of lambda t, is this one. I don't know if this is feasible. In accordance with the rule of the derivative of a product of two functions. The second derivative is a little bit boring, but believe me, I have to do the derivative of this. The rule which I apply from x to x dot and from x dot to x dot dot is always the derivative of a product of two functions. The derivative of this equals this one. You can verify at home, but believe me, we can see directly. We can see directly. It's boring, but it's not difficult. Plugging in x of t equal k of t multiplied exponential function up to lambda t, x dot, which is this expression, x dot dot, this boring expression, into here. We have this expression plus this one. We can see, for instance, this here is 2 times x dot. Here is x of t. All the rest here is x dot dot. Plug it in. Where, again, in order to understand more clearly here. I can cancel everything which is related to exponential function. I can cancel what is plus minus algebraically. We can see here x dot k dot minus k dot means minus 2 times k dot with this here. If you want, I can remark a little bit. And this here with this and this, right? Minus 2k of t plus k of t plus k of t cancel. This means at the end I have this. K dot dot equals 0, remain just this, which imply k dot equal k1. I think at the beginning of the semester we did something similar. from here remain k dot dot equals 0, which implies k dot equal k1, assuming that k1 is a constant. We have that k of t is k1 multiply t multiply k2. Assuming that k2 is a constant. Isn't it conservative constant? Absolutely no. Why that? Because at the end, I have as x of t. Do you remember was k of t, which is this one with these two assumptions, multiply exponential function up to minus 1t. Why that? Because lambda 1 and lambda 2 were equal and equal 1. Excuse me, minus 1. I told you correctly and then I forgot. Minus 1. This means with the assumption that x of t equal k of t multiply exponential function of lambda t, we have exactly this solution here. Why is not a conservative assumption k1 constant? Excuse me, I'm looking for the place now. I lost. I don't know now. Let me go ahead. It's not a conservative because I am able to satisfy the initial conditions with two constants. The initial condition 1 is here. Why that? Because x at time 0 was 1. X at time 0 was 1. Which implies that k2 equal 1. Why that? Because x at time 0 is 1 equal 0, k1 multiply 0 plus k2 multiply 1. This means k2 equal 1. Then if I consider the second condition, x derivative equals 0, at time 0, of course. If another time, no problems. I can put t exactly at time which I want or which I know. This is the derivative of this expression. And then I will put 0 here at time 0. If time is 1 second, I have to put nevertheless 0. If time at 1 second it's 0. And then instead of 0 here, put 1. A little bit more complex in the sense of the calculations, but it's the trivial structural, as in a trivial structural condition. K1 because t is equal 0, plus here remains K2. Yeah, please pay attention. I put something not so orthodox because here I have to put no, it's let me see. No, it's correct. It's correct. We can see also no? The derivative of this. No, it's perfectly calculated. It's this one. Huh? Minus 1 is here because it's derivative of the exponential function up to minus t. This means it's minus 1 multiply the exponential function up to minus t. This is the condition which we have if t equals 0 and x dot equals 0. This is k1, and here remain just minus k2 because of this minus here, which came from the derivative of exponential function up to minus t. The derivative of exponential function up to minus t, exactly this expression, minus 1, which multiply exponential function up to minus t. Consider k1 is equal 1. Is k2, excuse me, k2 is equal 1. We have thus k1 is also equal 1. Ready. This is the solution. We can see that this is a polynomial which multiplies the exponential function, which now covers everything, the two conditions, and also two dynamics. One is t multiply exponential function up to t, and another one is 1 which multiply exponential function up to t, but they are different. They are different. This solution here reflects the solution of the second order, because we have two eigenfunctions, exponential function up to t, and t which multiplies exponential function up to t. This idea of let me say, the product between two eigenfunction, let me say polynomial somehow, and exponential function. Let me see if I can improve this. And here we have in a general case, in which this is basically the general case. Let me see if I can say something more about that. Okay. I think yeah. If you calculate the eigenvectors at home, we will see the eigenvector are independent. They are independent. They are independent. Yeah, I don't want to insist. I don't want to insist on this. Here's the general case in which we can see that this instead of -1 is -k in this form here. Try to do at home. Try to do at home as an exercise. The same exercise, but considering t. Then we will review this exercise in the tutorial. We will review this exercise in the tutorial. I sketch a little bit the solution. The fourth answer, basically. This means 0, 0, t here. Remember the idea. X force is something structural, not exactly free. Like it's not wrong. It's not wrong. It's not exactly the free answer, but the free like plus and a particular function x star. This means free like. Do you remember this? This is exactly the structure of the free, but like, I mean, not exactly with the same K1 and K2. I called here K1 tilde, K2 tilde, because now the problem is not considering 1, 0, but 0, 0. But not only, therefore, because we have also the presence of this in the X4. Then we have to find here, basically, X4 star, which satisfy this. Try to do at home. Which order, which polynomial will, let me say, satisfy this condition. It's intuitive, if you think. I don't know if for you is visible. The combination of a polynomial with this combination must be equal t. Must be equal to. Do you remember the idea is to start with x equal t. Why not? Because we assume that the forcing signal is reflected in the solution. This means I can consider A multiply t plus b as a possible solution. This means here we have A multiplied T plus B. Here we have 2 times A, because the derivative of A multiplied T plus B is A, 2A, and here is 0. The second derivative of a polynomial of the first order is 0. This means 2A plus A multiplied T plus B equal T. This means A equal 1, because we have the unique element here is AT, and B equal 2, minus 2, excuse me. If you want, I write. But please do alone at home. Assuming that X, how you call it here? X star false. I proceed quickly because we have seen this. No, we have seen this. Excuse me. I assume that this is the form of the polynomial which satisfies, in a particular polynomial which satisfies this expression here. It's the permanent element which I want to calculate. This is going to 0, you remember? This is going to 0, we can see here. For t large enough, is going to 0, k1 tilde, k2 tilde as constant, because x free line. This is what remains if I have this force in here, remains in output. Assuming that this means x tilde forced of t is equal to A, did you agree? No? A and B is constant. Huh? Let me write somewhere. And the second derivative is 0, because the derivative of this constant A. Now, plugging in, as always, here, we have 0. This is the second derivative. Plus 2 times A, which is this, multiplied, plus this expression. Now, when this expression is satisfied, for A equal 1, because we have a T here and T here, and this implies 2A plus B equals 0. Did you agree? Because we don't have here any constant element. Excuse me. A equal 1 is clear because this element must be equal here, must be equal to this. AT must be equal to T. This means A equal 1. And then 2A plus B equals 0, assuming, in accordance with this, implies that, as I told you before, that B is equal minus 2, as I told you. Now, it's more explicit. No? Try to do at home. Anyway, now practically I did already the example, but to calculate x1 tilde, x2 tilde, you have to apply this general expression in which we already calculated this function here to obtain x1 tilde, x2 tilde, these two conditions. X times 0 equal 1, x derivative times 0 equals 0. Try to do. This could be a nice exam exercise. I will upload in my study, but we have already the solution here. If you consider again what we have here. Because we have basically everything here except K1 tilde and K2 tilde, but must be calculated, could be calculated, considering this initial condition. We did this many times. No? We did this many times. You have to calculate the derivative of this formally, analytically, but it's possible. This is known. This is known. What is this expression here? Of course, everything is in a function of K1 tilde and K2 tilde, but can be calculated with these two conditions. Okay. 1 second, let me reorganize the material, then we conclude today with lambda 1 equals lambda 2 equals 0. No? Because as I told you, lambda 1 equal lambda 2 is in a particular form. And in particular, excuse me, in particular form, if you consider lambda 1 equal lambda 2 equals 0. 1 second, of course. I have to reorganize the material, otherwise I lose everything. This is already, let me put also this, and then I come to you. I am almost ready. 1 second. At the beginning, yeah. At the beginning of the semester, let me, we calculated, if you look at the YouTube or the material, which you have in my study, excuse me, you have seen that you can see that we calculated together. 1 second. We calculated together the case of oscillations, but damped oscillations. You remember? Asymptotically stable, both in general. We obtain in a solution, we track. We have a steady state value, I don't know, 1, or it doesn't matter what, with oscillations. Remember, in case the eigenvalues or the exponential coefficient of exponential function are complex. Let me say complex means conjugated, no? Because you remember the Gauss theorem, the solution are complex if the solution complex is also conjugated. Let me now conclude this part, because now today was also the idea to analyze this particular lambda 1 equal lambda 2 equal 0, not only lambda 1 equal lambda 2. So lambda 1 equal lambda 2, not 0, we have seen already now exactly, is an interesting case, but it's not so dangerous in the sense, assuming that lambda 1 equal lambda 2 in any case, in this case, it's real, because if it's complex, we have two different values. With negative part, we have seen it's not a complex, let me say, situation, because first of all, negative part, but not only the eigenvectors are different. This means we have two different channels. It's not an exactly cascade form as I told you before. Let me show you now what happens in case lambda 1 equal lambda 2 equal 0 practically. Let me see a little bit practically, but not in cascade form. And then if you want, you can no, I would like to show you before I would like to do the cascade form. I would like to do it is more interesting, more because not in cascade form is the parallel form is the trivial, because it's not exactly what I want to show you. And then we have two parallel forms. This means we collapse this into not coupled dynamics. Let me show you. It's it's more easy to show you than to explain what I want to show. The last example, and then next week we will I will tell you about the nonlinear systems. It makes sense today to insist on eigenvalues because we will see next week in nonlinear system, we don't have eigenvalues. What we have, we will see. With an example, in order to have a feeling that the reality is not only in a linear system, or cannot be directly always approximated or to analyze as in a linear system. Okay, let me conclude the exam, the lecture of today with this example. We can see that the system is not decoupled, no? It's an interesting system. It's one derivative equal x2 derivative minus x1. You can put here also minus 2 times x1 and so on. But we can see that we don't have x2 here. Huh? Why am I insisting on this? Because if I have something independent of x2, the eigenvalues are not zero. The real part of the eigenvalue is not zero. Anyway, two initial conditions, doesn't matter which one. The second derivative of x1 is equal to the first derivative of x2, considering this expression here. And then considering this, we can write that x1 dot dot is equal to minus x1. Easy, no? I don't know if it's visible. In accordance with this, x1 dot dot is equal to x2 dot. If I do dot here, I do dot also here. Now, x1 dot dot is equal to x2 dot. But this means equal minus x1. I don't know if it is just observing what happens. No? If x1 dot dot is equal to x1 dot, because I do the derivative of this, I can write as x1 dot dot is equal minus x1. Why that? Because x2 dot, we can see here, equal minus x1. Or equivalently, you remember the idea to write everything which is here in form of matrix and vector. Again, here we have a system of second order, which reflects the dynamic of x1, starting from this couple dynamic of x1 and x2. Right? But in the meantime, as I did before, I can express this expression here with matrix and vector, in which we have here the vectorialization of these two information. Let me hold this left part. And here I realize this information on the right part, considering a transition matrix which multiply again the state vector. The state vector x1, x2. Again, why x1 and x2 are state variables? Because I am considering here the variations of them. The variation of them means the variation of the energy if you think about the possible representation of a physical system. We will see which one is. We will see which one. Then again, today I insisted a lot about this. I insisted a lot. Eigenvalue, let me go a little bit faster. Lambda I is this one minus A, exactly the transition matrix. To remember, today I insisted a lot on this. Now, determinant of this expression here, which is this matrix minus this matrix, is lambda squared plus 1 equals 0. No? So this multiply this minus this multiply this. We have this. Look, this from gymnasium, no? From our high school, means lambda 1, 2, lambda 1 equal root of minus 1, which is j, and minus root of minus 1, which is again j. Yeah. Lambda 1, 2, let me write in this short form, is plus minus j. J is root of minus 1. It's in an abstract expression, but it is. Of course, the same results can be obtained if I do exponential function, you remember, we have seen before. At the end, we have always the same solution. Believe me, I didn't put here, but I wrote that we can consider the two dynamics. X1 we have seen also before. We can build also the second dynamic of X2, and in accordance with this exponential function and so on, we can obtain. I think I have it here. Then all your equation. Yeah, I have it. It's a little bit boring, but I will show you. But here, the most important information is this. I can consider the dynamics of X1. I can consider the dynamic of X2. We reflect. It came, reflecting this came from the combination of the two dynamics. I have it here. A little bit boring, but I have it here. No, I thought that I have. I am proceeding here with the eigenvalues. No, look at this. This we have seen. X1 of t is k1 exponential function up to minus j of t plus k2 exponential function up to plus j of t. Do you remember lambda 1 is equal plus j, lambda 2 is equal minus j. This means I have to consider this combination. What is x2? Is the derivative of this. This means when I have x1, I have x2. But in general, we have seen also today, x2 is k3 exponential function of jt plus k4 exponential function plus jt. Yes, minus, yes, plus. Now, easy, I put it. Of course, this here can be considered k3. Yeah, can be considered k4. But this is exactly what I told at the beginning, is the easy form. x10 equal k1 plus k2. Why that? Because, as I told you at the beginning, we have two initial conditions. One is at time 0, x1, x10. One is at time 0, x2, x20. This means if this is the solution for x1, at time 0, we have x10 equal k1 plus k2. Why that? Because for t equals 0, this is 1. For t equals 0, this is 1. This means k1 equal x10 minus k2 from here. No? What about the second condition? But this is, as I told you at the beginning, this is the easy form, because x2 is this one, applying the rule of the derivative. No? K1 and K2 are constant, we assume to that. But you can ask me, but before with this K1, K2, we had some problems. Yeah. To be precise, we don't have problems, because it's true. Yeah, probably I was not so precise at the beginning, that the real part of lambda 1 equal the real part of lambda 2, but not the imaginary part. Probably I was a little bit fast. I mean, we don't have exactly lambda 1 equal lambda 2 equal 0. Is the real part of lambda 1 equal the real part of lambda 2 equal 0, but not the imaginary part. This means it's not exactly the case lambda 1 equal lambda 2 equal 0. It's the case in which the real part is lambda 1 equal lambda 2 equal 0. Not the lambda 1 equal lambda 2 equal 0. If you want, I can do later. Let me go ahead here. But it's extremely easy. But basically, I already did before. Anyway, this is the condition which came from here, which x20 is exactly this here, just algebraically considering this expression. This means if I do a lot of calculations, which basically is boring calculations, but we did something similar in a more boring, let me say, condition. The idea is to calculate k1 and k2 as a function of x10 and x20. You can see here, after these boring calculations. But look, this and this can be written in this form. This and this can be written in this form. And then I don't know if you remember, at that time, I considered the Euler equation, which this expression was cosinus of t, this expression was sinus of t. I don't know if I have time to tell you a little bit more in depth on the Euler equations, but you know from math. We have seen also this, I didn't demonstrate, but you remember when we did the case of oscillations. Here, the case of oscillations is particular. Why that? Because we have a permanent oscillations, something like that. No damped oscillation, permanent oscillation. The reason is we don't have here the function of x2. Excuse me for the confusion here. We have just real part of lambda 1 equal real part of lambda 2, but not lambda 1 equal lambda 2 equal 0. If I have a time, I don't know, I can, but you should know the Euler equation. This expression here can demonstrate mathematically. I haven't a demonstration. It's not so, it could be that I will do. Because we do next week the lecture, and then I will tell you, I need to recover in a lecture. This can be easy demonstrated using a differential equation. That's this is exactly cosine, and this is exactly sine. This is the case, real part of lambda 1 equal real part of lambda 2 equal 0. But lambda 1 is not equal lambda 2. No? 5 minutes. The case which I presented before is easier somehow because you remember lambda 1 equal lambda 2 equals 0. Basically, let me see if I can recall what I have now, the problem. 2 minutes and ready. This was the case. With the eigenvector, you remember, with the eigenvector which is depending. Yeah, in this case, it's independent. The eigenvectors of the transition matrix are independent. Try to do it over. The case was this, if I remember, was. But this is easier. With depending eigenvector. Try to do it home. I sketch here. We already seen this. Here, derivatives. The basic example with the eigenvectors depending. The eigenvectors again states the direction. The direction of, let me say, of the manifold of the solution. If they are depending, this means we have just, in this case, just one direction. We calculated together before, I don't know where it is, but you can find it. This is exactly the case, no? Which lambda 1 equal lambda 2 equals 0. What I showed before was not this, no? What the real part of lambda 1, the real part of lambda 2 equals 0, because we have two different imaginary parts, therefore this permanent, again, permanent oscillations. I will reconsider this. We have seen in the damping variation. Here is not the damping variation, it's just the permanent solution because physically we don't have the dependence of x2. This means we don't have friction. You remember, I told you a lot. We don't have friction, we don't have losses here. No? And we'll come back on this next week a little bit because the physical interpretation is extremely important. And this otherwise is just math. No? We just we have to a little bit advanced in our course. Try to do at home here. To look at the solution. Try to do this. This means I help you. Extremely easy. Did you agree that this equation here, we have two initial conditions? Of course, it doesn't matter which one. Do you remember before I told you something like that? Yeah, just general, doesn't matter what. With this initial condition, did you agree that this is the equation which reflects this dynamics? Yeah, split it in, let me say, two channels, two variables. We have two variables because I told you about the system here last time before, because physically we have two energies here. These two states. But the two states can be represented, the effect of two states is one. The system over the second order correspond to two equations, the first one connected. This is, I think we have seen, you have seen in math, considering the initial condition, try to do it. Oh, this is easier than I told you before. No? It's a ramp. No? You remember? It's a ramp. Think about this. The general solution, I sketched the solution, but try to do at home to demonstrate this. And try to calculate A and B generally with this. No? Of course, is in a ramp if this is not zero. No? Try to verify this. To remember the idea. The eigenvectors are depending. No? Free answer, no? Zero here. This you have a little bit better in the other slides. In the presentation, you have this. X1, X2 is in the middle. Yeah, is X2 derivative. And here we have X2 0, X1 0. Try to analyze this. If X2 0 is not zero, we have something which is growing up with the time. Of course, if this is zero, we have a constant. Try to analyze analytically, as a little bit I did in the presentation. But of course, this is it's easier than this. No, we have seen. Here, the eigenvectors are independent. Here, the eigenvector is depending. To summarize, we have seen also this case here with lambda 1 equal lambda 2 real with real part negative, eigenvectors independence, and the solution is the free solution. This one I told you about also. I will scan, I have here about the fourth solution. Okay, ready. Next week, I hope that you can come here. We will see together a little bit something related to the dynamics of nonlinear systems. No? In nonlinear system, we cannot use the eigenvalues. And today was a concluding lecture of this analysis of oscillations, eigenvalues, and so on. No? But we have seen many exercise with controller and without controllers. No? I mean, the dynamics of the controlled system we analyzed, we finished last week. No? That was a little bit summing up everything. I hope that you can come here next week, and then we will recover the lecture of last Friday. No, was out. I will tell you. Okay, Felix, Alexander, if you have a question, I'm here. Otherwise, I hope to see you next week here. Let me close here. You can find everything in my study. My study is updated now. It's updated. I will upload also this material of today. And in YouTube, you can, for free, look again what I told you. I hope it was not so difficult. I try to simplify everything. See you.